Hello class, let's talk about braced cuts, or also called as braced excavation. So in construction, where ground excavation is required with vertical or near vertical faces, example the basement of buildings in developed areas or underground transportation facilities at shallow depths below the ground surface. So if in a project which requires excavation with a certain depth, that might lead to shear failure that will cause erosion on these vertical faces. We need these faces to be protected by temporary bracing systems to avoid failure that may be accompanied by this settlement or by bearing capacity failure of nearby foundation. So we put bracing on these excavations to prevent these types of failure. So there are two types of brace cut commonly used in construction work. One type uses the soldier beam, which is a vertical steel or timber driven into the ground before the excavation. So this is the first type of brace cut. We use soldier beam. So the next one is we use sheet piles. They are of different types, but they serve the same purpose of protecting these excavations from failure. So in an isometric view, this is what it looks like for a braced excavation. So here are the parts of an excavation with bracing. So if we have here the sheet pile, then we have another layer for whale and the strut. What are these parts? We also have what we call the lagging. So when we define these parts, the lagging are horizontal timber planks which are placed between the soldier beams as the excavation proceeds. So these are your laggings. Okay, for a sheet pile, we have the sheetings. Then when the excavation reaches the desired depth, we now put the wales and struts are being installed now. The struts are compression members. So going back here, we put the whale and the strut that serves as our support for this bracing. So the usual concern in this topic is to determine the reaction on these struts, or the struts that serves as the support for this braced excavation. So say for example, we have here our sheeting, and these are the location of your struts. Okay, our goal here is to determine what are the reactions on these struts. So depending on to what type of soil that is present on the excavation, is that the type of diagram will depend also, or the type of stress diagram or the pressure diagram of the soil will also depend. So let's start first with sand. So in 1969, Peck provided the envelope of apparent lateral pressure diagrams for design of cuts in sand. So for cuts in sand, this is the apparent lateral pressure diagram for that, which is uniformly distributed from the surface up to the bottommost portion of the excavation. So we have a rectangular or uniformly distributed pressure for height h. So the equivalent apparent pressure, sigma A, has a formula provided by Peck, which is equals to 0.65 gamma HKA. Gamma is your unit weight, h is the total height of the cut, and Ka is the Rankine active pressure coefficient. It can be computed by using the angle of internal friction of the soil. Using this solution, tan squared 45 minus phi prime over 2. Or we can also use this solution, 1 minus sine phi over 1 plus sine phi. They are the same. Where phi prime is your effective friction angle. Next one is for cohesive soil or cuts and clay. Peck also provided the envelopes of apparent lateral pressure diagrams for cuts in soft to medium clay and in stiff clay. For soft to medium clay, the pressure envelope for soft to medium clay is shown in the figure on the condition that the computed value for gamma h over c, where c is your undrained cohesion for an angle of friction of 0, and h is the total height of the excavation or the depth of excavation. Gamma is the unit weight of soil. If it is greater than 4, we shall use this diagram. Okay, it is trapezoidal in shape. So it means from the surface measured from the top, it will start from a 0 pressure and we will reach the maximum pressure of sigma A, the apparent pressure, at a depth of 0.25 h. Then the rest will be uniform to the remaining 0.75 h depth. Okay, then to compute the value of sigma A or the apparent pressure, we have to use the larger of these two equations. The active pressure is either equals to gamma h, quantity of 1 minus 4c over gamma h, or a simplified form of this is gamma h minus 4c, or we use 0.3 gamma h. Another one for stiff clay. If the gamma h over c value is less than or equal to 4, we will use this apparent pressure diagram. Okay, it is also trapezoidal, but from the surface, we start from 0 pressure and up to a depth of 0.25 h, we reach the maximum pressure. Then, for a depth of 0.5 h, the pressure will be uniform. Then, up to the bottom, it will be reduced back to 0 pressure at a depth of 0.25 h. So, in computing the sigma A or the pressure, the active pressure, it is equals to 0.2 gamma h to 0.4 gamma h. That's the range of the value. Or we can simply use the average, which is equals to 0.3 gamma h. So now, how can we solve now the reaction for each strut? So going back in this figure, if we have cut in sand where it is uniform, okay, uniform pressure. So for us to determine the reaction on these struts, what we need to consider first is we have to remember that the type of support that we have on these struts are hinge support. So there's no present moment here on each points where our struts are located. They're just reactions. So also we have to remember also that here at the bottom part of this this bracing or this braced excavation is that we don't have a support here. It is considered as a free end. Okay, at the bottom, it is considered as free end, the same as the top if we don't have a strut there. So the bottom is a free end, the same goes at the top. So only the strut serves as your support here on braced excavation. That's why in computing the reaction on each strut, we can use section method where we can cut at any point on this uh, member, and we can compute the required value for each strut. Okay, we can cut here, we can cut here, as long as we could determine the required. So let's apply that to some sample problems here in this topic. For example number 1, as we refer to this figure, for which the unit weight of the soil is 17.6 kilonewtons per cubic meter and an angle of internal friction of 32 degrees, the cohesion is 0. The struts are located 3.66 meters on center in the plan. So we are required to determine the strut loads on A, B, and C level. So the 3.66 meter strut located on center in the plan is your spacing for the strut. So it means that in isometric view, if this is your strut, so we have a spacing of 3.66, okay, meter distance. So that's how it looks like, and so on. So let's focus on a single spacing of 3.66 meters in determining the required for a single strut. So it means that the equivalent tributary load for a single strut is just the center to center distance between the strut, or the area of concern of a single strut is just measured on each midpoint distance from the strut, or just equivalent to the respective spacing of the strut. So if our spacing is 3.66 meters, we will use that later on. Okay, I will just put here a distance of 3.66 meters. So now, since it is said here that the type of soil that we have is sand, so the pressure diagram that we're going to use is uniformly distributed or rectangular in shape. So to compute the equivalent value of sigma A, we have a formula of 0.65 gamma H Ka. So let's compute first the coefficient of active pressure based on Rankine's formula, where we have tan squared of 45 minus phi over 2, or we can also use 1 minus sine phi over 1 plus sine phi. So let's say I use this second one, where we have an angle of internal friction of 32 degrees. Okay. Rankine's active coefficient is 1 minus sine of 32 over 1 plus sine 32. Okay, so that is 0.307. Then I substitute it now to 0.65 gamma, the unit weight of soil, 17.6 kilonewtons per cubic meter, multiplied by H, the depth of the total depth of this excavation. So that will be equal to 1.86 plus 2.74 plus 2.74 plus 0.92. That's equals to, wait, this is 1.83. Okay, 2.74, 2.74, and 0.92. That's 8.23. 8.23 meters. Then multiply the Rankines active coefficient of pressure. Okay, 0.307. Okay, that's it. Then compute now. 0.65 times 17.6 times 8.23 and 0.307. The answer is 28.904. That's in kilopascal, kilonewton per square meter. Okay, so we're going to use this later. So then we are now ready to determine the reaction on each struts. So the first thing that we need to do is to have a section located on strut B. Okay, let's take this section and focusing on our member here. If this is a sheet pile, okay, having a section at point P, our figure now will be like this. So originally, if we have a figure of our member here, so this is blue, and this is your equivalent loading, which is rectangular in shape. Okay, so this one. With a value of QA, which sigma A, which is 28.904 kilopascal, and the strut reactions are 1.83. Say right here, reaction at point A, distance 1.83, and another 2.74. This is reaction at C, reaction at B. 2.74 and 2.74, and the last is 0.92 meters. Okay, let me just redraw this. 0.92. Here is your reaction at strut C. So now we take a section here at point B. Okay, having a section here, withdrawing this, let's say we have this one and another one. Okay, this is point B, this is point B. So it means that this is your reaction at point A. Still, we have the same value of sigma A. And since we have a section at point B, we have two values of reaction at point B. We have RB1 and RB2. Then reaction at point C, let's say right here. And this is your sigma A. Okay, focusing on the upper section right here, let's compute the value of the reaction at A by taking the moment at point B. Say clockwise is positive. So moment at point B, we have the first one is the reaction at A. So in this direction, we have reaction at A as positive with a distance of 2.74 as your moment arm. So 2.74 meters. Then it is subtracted by the equivalent force of this pressure. So in order to compute the equivalent force of the pressure, we need to multiply this active pressure to the area, okay, to this area of concern, which is the length and multiplied by the spacing of the strut, which is 3.66. Okay, and for a rectangular shape distributed load or a uniformly distributed load, the location of the equivalent concentrated load produced by this pressure is at the center of this rectangularly loaded area. So if this has a total of 1.83 is added by 2.74, so it means 1/2 of that is where your located distance of your moment arm. So let's compute first this total height, total depth from here to point B. 1.83 plus 2.74 is 4.57. Then you divide it by 2. It is where the location of 285 of your concentrated load produced by this pressure. Okay, so it means that the pressure is multiplied by the area or height of 4.57 multiplied by the spacing, okay, the width or the spacing between the struts, which is 3.66 meters, then multiply to the moment arm, which has a distance of 2.285 or the 1/2 of 4.57. Okay, 2.285 meters equals to 0. So let me substitute the value of the computed stress or pressure, 28.904. 28.904 kilopascal multiplied by 4.57, 3.66, and 2.285 meter equals to 0. So I will just directly solve the reaction at A using my calculator. Okay, let reaction at A be the variable x. 2.74 minus 28.904 times 4.57 times 3.66 times 2.285 equals to 0. Then we solve it. Shift calc. The reaction at point A is 403.17. 172 kilonewtons. So that's the answer for reaction at A. So that's your load at strut A. Then from that, focusing again on the upper section, we can compute the reaction at B1, RB1. So for the reaction at B1, we just take the sum of forces along the horizontal equals to 0. It is much easier than we take the moment at this point or at any point. So focusing again here, taking the sum of horizontal forces, going to the right positive, we have reaction at A as positive, then added by reaction at B1, then subtracted by the equivalent concentrated load by this applied pressure. So to compute this nga, that active pressure is multiplied by the depth 4.57 and the spacing. Okay, this will be your equivalent force. Let's say PA 3.66. So here I will just write here the solution where the pressure is multiplied by 4.57, and 3.66 to determine the equivalent concentrated load. Substituting the value of A, reaction at A, 403.172 kilonewtons, is added by reaction at B, then subtracted by sigma A, 28.904 kilonewtons per square meter, 4.57, and 3.66 meters is equals to 0. So again, I will just directly solve the reaction at B using my calculator. Okay, 403.172 plus x as your variable, then 28.904 times 4.57 times 3.66 equals to 0. Okay, so the reaction at B1, this is 1, is 80.28 kilonewtons. Okay, that's not yet the reaction at strat B because we have the second reaction at B at this lower section. Okay, so now let's proceed on this section right here. So the first one that we could identify here is the reaction at C by taking the moment again at point B. So let me just rewrite the dimensions between reaction B and reaction C. 2.74 and 0.92. Okay. Taking the moment at point B, here. Okay. Moment at point B, clockwise positive. We have reaction at C. Okay, take the moment here, clockwise positive. Sigma A therefore is positive, multiplying it to the total depth here to determine the equivalent area first. We're going to multiply on the pressure to find the equivalent concentrated load. So 2.74 plus 0.92 is 3.66 meters. So that's 3.66 meters, the depth, multiplied by the spacing, 3.66. Then we multiply it to the moment arm. Okay, so if this is your equivalent concentrated load, we need to find this distance, which is just 1/2 of 3.66. Okay, for a uniform load. 3.66 meters divided by 2. Okay, that's for the moment due to this pressure. Then the second one is the reaction at C, clockwise. So in the direction of counterclockwise is reaction at C, that will be negative. So the distance is 2.74 meters equals to 0. Okay, substituting the value of sigma A, 28.904 kilopascal multiplied by 3.66 meters times 3.66 meters times 3.66 meters over 2 minus reaction at C times 2.74 meters equals to 0. So the reaction at C therefore is, computing it again, 28.904 times 3.66 times 3.66 times 3.66 over 2 minus RC times 2.74. equals to 0, that is equals to 258.595 kilonewtons. Okay, that's the reaction at C. For reaction at B, number 2, reaction at B2 is just taking the sum of forces along the horizontal. Okay, so we have reaction at B2 plus reaction at C minus the equivalent, okay, equivalent active force. So this is just 3.66 times 3.66. Okay, so 28 or sigma A times 3.66 times 3.66 meters is to 0. Reaction at P2 therefore is equals to, let's just transpose all of this. The reaction of the sigma A is 28.904 kilopascal times 3.66 times 3.66. This will be negative. Now the reaction at C, 258.595 kilonewtons. Therefore, the reaction at B2 is 8.904 times 3.66 times 3.66 minus 258.595, 128.591 kilonewtons. So, for the total reaction at point B, reaction B, just take the sum of reaction at B1 and reaction at B2. B1 is 80.282 kilonewtons added by 128.591 kilonewtons. The total reaction at point B is 80.282 plus 128.591, 208.873 kilonewtons. So here are your answers for the reactions at point A, point C, and strat at point B. Okay, that's for the example number 1. For problem number 2, a brace sheet pile for an open cut and a stiff clay is shown on the figure. The struts are spaced longitudinally at 4 meters center to center. Okay, that's the spacing of the strut. Now we are required to compute the strut loads at point A, B, and C. Okay, the reaction at A, B, and C. Given the unit weight of the soil, 17.29 kilonewtons per cubic meters, and QU, which is 96 kilonewtons per square meter, or the unconfined compressive strength of the soil, QU. Okay, so here's the spacing, here's the interval for each strut from the surface to the strut A, 1.5 meter, then 3 meter, 1.5 meter. So it is said there that it is a stiff clay. More likely the diagram for the stress or the pressure of the soil is the shape of trapezoid. But we have to verify it first using the solution gamma H over C if it is greater or less than 4. So by computing it, 17.29 kilonewtons per cubic meters is multiplied by the total height or total depth of the excavation, which is 1.5 plus 3 plus 3 plus 1.5. That is equivalent to 9 meters. 9 meters over the cohesion. So the cohesion can be computed using this confined compressive strength, where the cohesion C is 1/2 of that unconfined compressive strength. So 96 over 2 kilopascal is 48 kilopascal cohesion. So this is 48 kilopascal. The equivalent value therefore of gamma H over C is equals to 17.29 times 9 over 48. So that's 3.24. 3.24 only. So it is less than 4. Therefore, we are correct in assumption that the shape is in trapezoid and it varies from 0 to the surface up to a depth of 0.25 h, then uniform for a depth of 0.5 h, then going back to 0 pressure again at the bottom. So let's draw the pressure diagram now. Okay, like this. Okay, so this is your pressure diagram. So the depth of this one is 0.25 h, or h is 9. 0.25 of 9 is equals to 2.25 meters. Then 0.5 h, okay, or 1/2 of 9 is 4.5. Another one, 0.25 again. Okay, now this is your pressure. So what will be now the sigma A? So the sigma A is, it ranges from 0.2 gamma H to 0.4 gamma H, but by average it is 0.3 gamma H. So 0.3 multiplied by gamma, the unit weight of the soil, 17.29 kilonewtons per cubic meters, times the height of the soil, 9 meter. So sigma A is 0.3 times 17.29 times 9. Okay, it's 46.683 kilopascal. Okay, that's the pressure, sigma A. So that's 46.683. So what we're going to do now is to have a section. The easiest way to section this one is at strat B. Okay, and coincidentally it is at the midpoint. Okay, since the shape is symmetrical, point B is the midpoint of this member, and by taking the section, the figure now is like this for the upper section, and for the bottom it's just the same. They are symmetrical. Okay, let's say this is the upper section. Okay, here. So it has a distance of 2.25 for this one, 2.25, and the remaining distance is 1/2 of 4.5 is also 2.25. Then for the location of strat, that is 1.5, somewhere here. Reaction at A, distance of 1.5 meters. Okay, and the distance of 3 meters. Okay, focusing first here. We have reaction at B, right here, RB1. So taking the moment at point B again, clockwise positive, right here. So we have reaction at A multiplied by the moment arm 3 meters. Then here we have a trapezoidal shape uh, pressure. So we can directly solve the equivalent uh, force of this trapezoidal shape pressure, or we can separately solve the uh, equivalent force of the triangle and the rectangle. So we can solve equivalent force of this triangle, the upper triangle, and this rectangle here separately. I think that's the easier way. So first, let's have this rectangular shape pressure by simply multiplying again sigma A to the area. Okay, subtracted by sigma A times the depth is only 2.25. Okay, for this rectangle here, 2.25. Then multiply it to the width or the spacing between the struts, which is 4 meters. Then multiply it to the moment arm, which is for a rectangular or uniformly distributed load. It's just at the midpoint, or 1/2 of 2.25 distance. 2.25 meter divided by 2. Then let's now go here for the triangular load. So for triangular load, if this is your maximum pressure, which is 46.683, we just take the half of it. 1/2 of sigma A is multiplied again to the depth 2.25 and the spacing, which is 4 meters. Then multiply to the moment arm. So for a triangular shape pressure, the location of the force is coming from the base, measured 1/3 of its depth, which is 2.25. Okay, that's the distance from the force to the base. Then we just add up 2.25. So if I will directly write the solution for the moment arm of this triangular load, we have 1/3 of 2.25. 1/3 of 2.25 meter is added by 2.25. 2.25 meters. Okay, so this equals to 0. We can compute now this reaction at A. So let me just rewrite the solution by replacing the value of sigma A, 46.683 kilopascal, to the solution. Okay, the reaction at A therefore is RA variable x times 3 is subtracted by 46.683 times 2.25 times 4 times 2.25 over 2 minus 1 half 0.5. 46.683 times 2.25 times 4 times, I think this is 1/3 of 225 plus 2.25. Okay, equals to 0. That is equals to 367.628. 629 kilonewtons. That's for the reaction at A. Okay, reaction at A. For reaction at B, take the sum of forces along the horizontal. Going to the right is positive. So we have reaction at A plus reaction at B1 subtracted by the equivalent force of this rectangular shape here, or simply this one, the solution right here. Okay, let me just copy that. 46.683 kilopascal times 2.25 times 4. Then subtracted again by the triangular load, this one. Okay, exclude the moment arm. What is required is just the force. 46.683 kilopascal times 2.25 times 4 equals to 0. So reaction at A, let me just substitute this one here. Okay, let's substitute. Okay, let me just put an arrow. I will substitute that here, and using the calculator, we have reaction at A is 367.629 is added by reaction at B1, unknown, so that is our variable, minus 46.683 times 2.25 times 4 minus 1 half of 46.683 times 2.25 times 4. Okay, that's it. That is equals to 105.037 RB1. Okay, let me just, sorry, that's 262. Okay, 260. Okay, 262.591. RB1 is 262.592 kilonewtons. Okay, now after we have answered the upper section, we can solve the values for the lower section. But here, it is coincidentally the figure that we have here is symmetrical. And knowing that the bottom of this excavation has no support, okay, this is a free end. So it goes to show that we have an identical values for the upper section here. If we are going to compute the values for the reaction A, it will just be identical as to the reaction at C because their distances are the same, 3 meters, 3 meters, 1.5, 1.5. The same goes with the pressure diagram, which is also symmetrical, trapezoidal. So what we can compute here is just the same for the value of reaction at C. Okay, for the reaction at C as well as the reaction at B2. So let me just redraw. Okay, just redraw the RB2. Okay, so this is RB2 and your RC. And we have the same value of sigma A, 46.683. And the depth of this one is 2.25. This one also is 2.25. So they are identical. So it means that the reaction at A would just be equals to the reaction at C. Okay? Since the pressure and location of struts are symmetrical, okay, we can conclude that the value for the reaction at A and C are just the same. So the reaction at C is 367.629 kilonewtons. Okay, this is reaction at C. So the reaction at B2 also is the same as reaction at B1. RB1 also is equals to RB2. Okay, it is only for this example only because they are the same distances, they're symmetrical. But we can also always check it by manually computing it again by taking the moment again at this point at point B and compute for the reaction C, and take the sum of forces along the horizontal to compute the reaction at B2. It will just arrive to the same answer. So therefore the RB2 is equals to 262.592 kilonewtons. So now that reaction at B therefore is equals to the sum of RB1 and reaction at B2, or simply multiply 262.592 by 2 times 2. Okay, so the reaction at B is equals to 262.592 times 2 is 525.184 525.184 kilonewtons. So that's the answer for this particular problem for the reaction at strat B. Reaction at strat B, reaction at strat C, and reaction at strat A. For example number 3, a braced cut shown in the figure. It has struts A, B, and C are spaced 5 meters center to center using Peck's empirical pressure diagram, and the soil is medium clay. We are required to determine the loads on strut A, B, and C. So the medium clay properties are, we have the unit weight of the soil 17.5 kilonewtons per cubic meter, cohesion of 30 kilonewtons per square meter. So first, verify if gamma H over C is less than or greater than 4. So gamma is 17.5 kilonewtons per cubic meters times H, the total depth of the excavation. That will be equals to 1 plus 3, 4, 7, 8. That's 8 meters. This is 8 meters over the cohesion, which is 30 kilopascal, kilonewton per square meter. So 17.5 times 8 over 30 is equals to 4.67. 4.67, that is greater than 4. So the diagram of this pressure is of this shape. Okay. Okay. So this is 0.25 of 8. So 1/4 of 8 is 2 meters, and the remaining is 6 meters. Okay, so if this is 2 meters, let me just exaggerate the drawing. 2 meters is about here. Okay, let's draw the dimension. Okay, this is 6 meters and this is 2 meters. So now, this is your pressure. Let's now compute the sigma A. Okay, what will be the pressure? The value for this one, it's either gamma H minus 4C or 0.3 gamma H, whichever is larger between the two. So comparing the values for 17.5 kilonewtons per cubic meters times 8 minus 4 times 30 kilopascal, that will be equals to 17.5 times 8 minus 4C, 20. So sigma A equals to 20 kilopascal. On the other hand, we have sigma A is 0.3 gamma H. So 0.3 times 17.5 kilonewtons per cubic meters times H, which is 8 meters. So 0.3 times 17.5 times 8, 42 kilopascal. So we will use this one. Okay, use 42 kilopascal as your value for sigma A. 42 kilopascal. So next, we are about to take the section at B. Take the section at B so that we will be able to determine the required reactions at A, B, and C. So taking this section above in the shape of trapezoid also. Okay. Okay. Has a depth of 2 meters. This one. So it has a total of 4 meters. So 2, 2. This is also 2. Okay, this is your pressure. This is sigma A. And we have reaction at A at a distance of 1 meter. So 1 meter is right here. Okay, reaction at A. And reaction at B1. Okay, so this has a distance of 1 and 3 meters. Okay, taking the moment at point B, here, this location of strata at point B, strata at A, moment at B, clockwise is positive. Okay, take the moment here. We have reaction at A is multiplied by the moment arm 3 meters, subtracted by the equivalent forces by this trapezoid. So the first one is we use this rectangular shape pressure. So we multiply sigma A by the depth 2 meters and the spacing of the strut, which is 5 meters. Then we multiply it to the moment arm, which is 1/2 of 2 meters. So this is 1. Then subtract again for the triangular pressure. Okay, the equivalent force of this triangular load. It has a moment arm to be measured from the base, which is 1/3 of its depth, which is 2 meters times 1/3. Then we just add up 2 meters, which is measured from point B when we find the moment arm. So that is 1/3 of 2 added by 2 meters. That's the total distance of the moment arm. So for a triangular load, we take the 1/2 of sigma A and multiply the depth, which is 2 meters, the height, and the spacing, which is 5 meters. Then multiply the moment arm, which is 1/3 of 2 meters added by 2 meters again. So let me just substitute again the value of the computed sigma A, which is 42 kilopascal, to the solution. So now we write the solution. This is equals to 0. We can now compute the variable, which is the reaction at A. So again, I will directly solve it using the calculator as the variable x, which is the reaction at A, minus 42 times 2 times 5 times 1 minus 1/2 of 42 times 2 times 5 times 1/3 of 2 added by 2. That is equals to 0. So let's solve for x. This equals to 326.667. 326.667 kilonewtons. That's the reaction at point A. Reaction at B, 1. Let's take the sum of forces along the horizontal equals to 0. So RA plus RB1 minus the equivalent forces of the pressure of soil, which are the values for this one and this one. So we will just copy the solution for that here. 42 kilopascal multiplied by 2 meters times 5 meters minus 1/2 42 kilopascal times 2 meters times 5 meters. That is equals to 0. Substituting the value of reaction at A, 326.667 kilonewtons, plus reaction at B1 minus 42 kilopascal times 2 times 5 minus 1/2 of 42 kilopascal times 2 meters times 5 meters equals to 0. So the reaction at B1 is computed as 326.667 plus RB1 variable x minus 42 times 2 times 5 minus 1/2 of 42 times 2 times 5 is equals to 0. That is equals to 303.333 kilonewtons. So that's RB1. Next, we now focus on the lower end of this section, which is rectangular in shape. So, we redraw it. This will be the figure. And we have reaction of B. This is RB2. Then the reaction at C is 3 meters. Okay, 3 meters from point B. And the remaining is 1 meter. So this is a uniform load. sigma A. Sigma A is equals to 42 kilopascal. And we have a total depth of 4 meters. So taking the moment at point B again, right here, take the moment clockwise, positive equals to 0. We have a positive pressure. A is multiplied by the total depth 4 meters. Okay, considering this full load, multiplied by the spacing, which is 5 meters. Spacing is 5 meters, and subtracted by RC times 3 meters equals to 0. Okay, we forgot the moment arm. Okay, for the force due to the pressure of soil, that is 1/2 of 4, 2 meters. So let me just add it up here. We have a 2 meter. Okay, this is 2 meters. That's multiplied by 2 meters. So now, computing the value of RC, we substitute 42 kilopascal to sigma A, and RC is the variable. 42 times 4 times 5 times 2 minus x times 3. That is equals to 560. Okay, the reaction at C is 560 kilonewtons. That's the answer for reaction at C. And for reaction at B, we take the sum of forces along the horizontal. Going to the right, positive RB1, RB2 plus reaction at C is subtracted by the equivalent force, which is this one, 42 times 4 times 5, 42 kilopascal times 4 times 5 equals to 0. So RB2 is just equals to 42 kilopascal times 4 times 5 subtracted by reaction at C, 560 kilonewtons. So the reaction at B2 is equals to 42 times 4 times 5 minus 560. That is 280 kilonewtons. For the total reaction at B, the reaction at B therefore is reaction at B1 plus reaction at B2 is equals to 303.333 plus 280 kilonewtons. So reaction at B is equals to 280 plus 303.333, 583.333 kilonewtons. So that would be your final answer for the reaction at point B. So these are your answers for reaction at A, reaction at C, and reaction at B for a medium clay type of soil for a braced excavation. So that ends our lecture for this video.